And then there was another mistake in the eigenvalue of the pairing Hamiltonian. So it was SS plus 1 minus MS times MS minus 1. I wrote plus 1. Okay. But then everything else should be more or less okay, I hope. So we discussed conservation of seniority and how this is now can be reformulated as a condition on the two-body matrix elements. And here is the example for the G9 half, right? And then here, these are general relations. So this is always calculating this expression here for different values of J, which can be integer. Then you have the bosons, or small j, right? And for the fermions, it's half odd integer, so you have these relations for the different shells. Okay, so this is now, this is actually a very neat derivation due to De Chalit and Talmy. So where the conservation of seniority is just, it boils down to whether the interaction satisfies certain conditions or not. Okay, so now you can say, well, again, this is only for identical nucleons, right? So I'm talking about semi-magic nuclei, right? Either neutrons or protons, and we will see examples of that in the exercises. So then you have to ask the question, is seniority conserved in nuclei? And so, well, so as I said, pairing interaction conserves seniority. Then I argued, but there is a much larger class of nuclei, of interactions that conserve seniority. And so we will also show this afternoon that, or at least not prove, but we will sort of indicate that if you take a delta interaction, then a delta interaction also conserves seniority. So this we will show with a particular example. Okay, and so since the delta interaction, it's a better approximation, it's not so bad as an approximation to the true, the realistic interaction between identical nucleons, you can sort of say that semi-magic nuclei seniority is conserved to a good approximation. And this also we will sort of test this afternoon with an example. Okay. Let me now go to a few words about generalized seniority models. And basically they are of two types. There are several generalizations possible, but two important ones. One is if you consider non-degenerate shells. So I said quasi-spin formalism can be easily extended to degenerate multi-shells. But what about non-degenerate shells? And so here I will say a few words about this integral pairing models, Richardson-Gaudin, and then I will say also something about generalized seniority due to Talmy. And then there is an obvious generalization. I mean, nuclei consist of neutrons and protons. So what happens if we consider a pairing interaction between neutrons and protons? How can we introduce isospin into pairing models? So this I will not discuss at all, because this is a topic that will be covered by Augusto Machiavelli this week. So he will arrive today. He will talk about this, I think, tomorrow and Thursday. Okay, but just he probably will not mention, well, he might mention that, I don't know, but there are quasi-spin techniques which you can apply if you have only T equals 1 pairing, so sort of the pairing that I discussed so far. But if you have neutrons and protons, you have also pairing in a different channel, which is T equals 0. And so both of those cases can be treated by the techniques that I mentioned here. Okay, so but let me spend a few minutes on these integrable pairing models. And so now the Hamiltonian we want to solve is a little bit more involved. So we want to consider several orbits. Let's say this is a number operator, and then a pairing interaction like this, a pairing interaction with a constant strength, right? So you have several orbits. In principle, they can have different single particle energies, so this will be epsilon 1, epsilon 2, and so on. And then you have a pairing interaction, so two particles, a pair of particles here, a pair of particles here, they interact, and the interaction is independent of the orbits they're sitting on. Okay, that's not such a realistic approximation, but that's the best you can do. But it turns out that this is a solvable, this is an integrable Hamiltonian. And by that I mean you can write it as a sum of operators that commute. I'm not going to do the derivation of this. The only thing I would like to do is to give you a feeling of this by looking at a simple case, namely two particles. So let's look at the case of n equals 2. This is sort of instructive, it's not too complicated, and it gives you a flavor of what is happening. So I construct a state, I will give it an index alpha, right? And written explicitly, it's a straightforward generalization of what the S pairs we considered up to now, namely, instead of having a combination of pairs of particles in the different shells with the same coefficient here, we take here arbitrary coefficients. This is sort of, this alpha means that it is defined through these coefficients, okay? And so this guy here, if you remember, this is just a dagger j equals a dagger j coupled to 0. Okay. Yes. Okay, so now let's assume that we have alphas such that these states are eigenstates of the Hamiltonian. So E okay, this you probably are familiar with, so you put two particles, there are only two particles in this orbit. Of course they can be here, right? But they can also, they have some probability of being in this level, that level, that level, and so on. And these probabilities are proportional to those coefficients here. And so now you just take this Hamiltonian with non-degenerate orbits with a certain strength G, okay, and these alphas will come out of this eigenvalue problem, and the solution right, I will give one intermediate equation. This is 2 epsilon j this is the secular equation. E alpha j, and then you can solve the alpha j's up to a constant. You can solve the alpha j's from that, namely alpha j is proportional to, well, I can just forget g 1 over 2 epsilon j minus e, and then you put it back in and you get an equation which looks like sum over j plus 1/2, then here 2 epsilon j minus e is 1 over g. Okay, so this is two particles. In the notes you have a few more steps, intermediate steps, but it's basically it's simple algebraic manipulations. Okay, so these are the unknowns, right? So you want to solve this equation. G is, I mean, this is the strength of my interaction. So in nuclear physics this will be a positive number, so it's an attractive pairing interaction, and so the epsilon j's, these are the single particle energies. Okay, and so you have to solve this equation, and this you can do graphically. Let me do it here. Yes, this is graphic solution of this problem. Right. So what you have on this axis is here the vertical lines, they correspond to the choices. I think it will be 2 epsilon twice the single particle energies. Okay, and then this blue curve here, this is just this quantity here, right, as a function of E, the energy, right? And so you want that this quantity equals 1 over g, and this line here is precisely g to the power minus 1. Now I have an attractive pairing interaction, so this comes back to the yes. The particle number
nj, yeah.
Yes, it does. It will not commute with S plus. I mean,
Yeah, and you said that this S plus operator commutes with the Hamiltonian.
did I say that? Then
You've written it as an eigenstate. I think it's the line he's. I think you said they have the same state.
this is an eigenstate of the Hamiltonian.
This is what you said. You didn't say.
Yeah.
Yeah, and you said that this S plus commutes with the Hamiltonian.
It will not commute with the Hamiltonian. I mean, if I said that, then I've said something wrong. I mean, I think I've only said that this is an eigenstate of the Hamiltonian.
You said that.
Okay, maybe I misunderstood.
Whatever I said, I retract it. So it's not it's an eigenstate of the Hamiltonian, but it doesn't commute with it, because you can see, right? Because this S plus, these are number operators. You create two particles. So okay. Oh, I said you can write. Yes, I agree. You can write it, the Hamiltonian, as a sum of commuting operators. This I said, but these operators are not the ones you see here. They're more complicated. So and that this derivation I will not do because that's a long. Okay, yes. So I understand your remark now. So you listened. Good. Okay. Right. So it can be written as a sum of commuting operators, but that's okay. Let me get back to this graphical solution. So it's 1 over G here. The G is positive for an attractive pairing interaction. And you see, if I increase the G, I will decrease this line, and there will be one state which comes low in energy. This is the same thing as Rick mentioned in the first week. This is the collective state, right? And one can actually show that if this G in the limit of G going to infinity, that well, the coefficients of these collective states become essentially constants, and so you will get to a situation where these alpha J's become 1, right? And you get to the situation of quasi-spin. Yes.
That E equals 0 line, does this correspond to a bound state, or is the definition a little maybe different? I'm just wondering if the equals 0 line looks like we're guaranteed to have a bound state in this interaction.
Oh, this can be shifted. You see, you can shift all those energies up and down with a constant, and it will not change anything to the problem.
Okay.
So, but essentially, I'm talking here about bound state problems, right? So no complex energies. And I guess in this example, I must have put the first energy here at 0, but I could have put it at minus 100, so it wouldn't change. The other point is that, for instance, if you now take a repulsive pairing interaction, so you go to the other side, you see that your collective state is not here. Your collective state actually gets here. It gets pushed up in energy. And that is a property one has to keep in mind. For instance, giant resonances. They can be understood from that point of view. Okay. Now, this was for 2 particles. What do you have to do for n particles? Then you get an additional term which I have to check signs and things like that. Is 1 over G. And what is important that yeah, I don't have any. So this is now for general n. I can erase everything here. And this will be an eigenstate of an Hamiltonian. this is quite strange equation. So you have your single particle energies. These are the unknowns, and so you have actually n particles, so you have n over 2 pairs. Okay, this is for an even nucleus, for a system of even particles, I should say. So then you have an index that runs over the n over 2 pairs. Okay, and these are the single particle energies twice, and this is now a quantity which depends on the p, right? So you don't have, remember that in the degenerate case you had a ground state which was of this type, right? You had sum over j to the n minus 2, okay, acting on the ground state. Right? What is replaced now is not identical pairs of particles, but with some kind of a factor. This factor we more or less understand from the two-particle analysis. Okay. The only point is that here, I should say P, right? Here we have now a more complicated equation. This was there in the two-particle case. That was there, but now we have this term, which is additional, and which is sort of a repulsive, I don't know what is the interpretation, but this is an additional term which comes up in the many particle case. Okay, and these are called, this is called the Richardson Godin equation. Okay, these are nonlinear equations. You have to solve for the unknowns, right? EP, and then you have a solution of your pairing Hamiltonian.
So is this the result of what it means to be integrable?
Yes, yes. So the fact that you can write this by manipulating in some fashion, by manipulating this as a sum of commuting operators, you can get to this result. It's not trivial. So this is, and what is nice, you can generalize this. You rely on the fact that you have quasi-spin algebras for each of the levels separately, okay, which are SU2. But then I showed you have something similar for neutrons and protons, which is SO5, or if you have more complicated pairing interaction, SO8, and you can do the same analysis in those more complicated situations. So you have Richardson equations for a system of neutrons and protons with a pairing interaction, or a system with two different pairing interactions, t equals 0, t equals 1. These have been derived but not really studied in detail. Okay, so this is still not actually what you want to have, because this, as I said, this is a constant pairing interaction, right, between all levels, and you might want to do something a bit more tricky, which is this. That would be very nice if you can solve this case where you say j prime. I have pairing strings that depend on j and j prime, and then j prime. Okay, so here you would have pairing strings that depend on where the two pairs are sitting, and you have actually physically you have a situation where if the two particles are sitting in the same orbit, you expect that this strength will be larger than when you have a pair of particles here and a pair of particles. So it drops off, right? And this, well, I don't know any analytic solution on that. What you can have is if it is separable, right? If you have jj prime equals a strength associated with orbit j times a strength associated with orbit j prime. This is a separate pairing interaction. And so there are some analytic solutions known for that. Okay, so this more or less is a brief sort of overview of more complicated pairing Hamiltonians. Okay, and this is still something where people derive new results. Like for instance, this situation with neutrons and protons. Okay, the equations have been derived, but I don't think they have been studied in much detail. Let me now come to a last topic concerning pairing. And this you frequently encounter if people talk about pairing. And there is a lot of confusion concerning this. And this is something which is called generalized seniority. Okay. And so I convinced you, I hope, that seniority is a quantum number which is conserved by the pairing interaction and by much more general interaction. But the general interaction actually is not solvable. It has the only property that the eigenstates, if it's conserved seniority, the eigenstates can be labeled with seniority. But it doesn't mean that you can solve analytically all the states. Okay? This now is a trick that was, or a situation that was proposed by Talmy like 40 years ago. And let me put here a Hamiltonian, and he just, so this is GS is for generalized seniority. He just supposes that he has a linear combination S alpha, okay, which is an eigenstate of the generalized Hamiltonian. Okay. And then he assumes, in addition, a double commutator to be okay. He assumes those two properties. This is Talmy, yeah? In 1971, actually. And this is not there is no algebraic structure related to this, okay? But what you can show is that if these two properties are valid, and this is, I still don't understand very well why this happens, but you have a solution which you can write. So n E0 was defined there. And so now you have to see the difference with Richardson solution. In the Richardson solution, you don't have this property because you have a superposition of n over 2 pairs, but the pairs are different. They're not identical. Okay? They depend on this factor here, and the energy P changes from pair to pair. Okay. If you impose those two conditions, then you find that you have an eigenstate, and this is an exact result, it's not an approximation. The eigenstate of this Hamiltonian, whatever the conditions mean, is always the eigenstate with a constant structure. But not, I mean, this written explicitly, remember, it's sum over j, alpha j, s plus j. Okay? So the alphas are not necessarily 1, as we had in degenerate orbits. No, they can be anything, but there should be a solution of this Hamiltonian. There must be a factor delta missing. Yes, here. Okay. What was I saying? Yes, and there is now an approximation which is called the generalized seniority approximation. And this is basically saying, well, I diagonalize my two-particle system, I find my coefficients alpha, and then I assume that this will be an eigenstate of my Hamiltonian. Right? Of course, if you want to be rigorous and exact, then you should check that your Hamiltonian satisfies this double commutation. Yes?
Could you define this Hamiltonian, or say what is it?
You can look at this paper and he derives the conditions. Why? What are the conditions on the interaction, right? What should, because now you have several orbits, so you have a complicated interaction which is defined for each orbit, and then interactions between particles in different orbits. So this is a complicated interaction. He derives the conditions from this. What does it? But they're very complicated. So I don't have a feeling of what this double commutator actually means. It's a mathematical derivation, but at least to me, maybe some people have studied this better than me, but this, yes.
So even if it's foggy, what it means intuitively, can we get some sort of sense of how strong this requirement is? Like, is this something that is very rare and nearly useless, or is this something that is seen often?
I would say the approximation is used frequently, in the sense that you will assume a condensate, even if your Hamiltonian is not a pairing Hamiltonian, right, and deviates strongly from it, you assume that you can have a ground state of this type, right, where the alphas, you might get it from a two-particle problem. You might say, well, I'm doing a minimization of my Hamiltonian. Right, I have a state like that, and this is a bit more general. I guess I can put S minus here and minus 2, right, and then I minimize with respect to the alphas, right. This would be exactly the same if n equals 2 for two particles. This is an eigenvalue problem. Here it is a minimization problem, right? And this is frequently done, but I have to admit, people usually don't check whether this condition is satisfied. So then it is an approximation.
Maybe there's some sort of connection between how badly this double commutator is broken to how quick convergence happens or something.
Certainly there will be a connection, but as I said, these lead to very complicated equations which I never had an intuitive understanding of.
So what
Yes.
do you mean by generalization of seniority in that case?
Oh, because you have still this structure, right? This was sort of the hallmark of the seniority scheme, that in the ground state, right? This is for the ground state, that in the ground state your ground state as n over 2 identical pairs. And this is very similar to that, except that now it's not just a summation with coefficients 1, but with arbitrary. Yes?
Can you talk about what was the motivating factor for going in this direction
Oof.
from the why is this something?
I'm not Talmi, huh? So, and Talmi was somebody who, well, is somebody, I should say, I'm sorry, is somebody who had very much an algebraic approach to things. I mean, and he derived formulas, and then people asked what they mean, but okay, I don't know why he would. I think he must have realized the importance of this kind of formula in the usual pairing case, right, with degenerate orbits, and then said, well, can I derive a condition that comes back to this, right, but is more general? Because you see, the generalization is the fact that you can have probabilities like BCS probabilities for this, have orbits which are more occupied than other orbits. This is completely compatible with this scheme. Yes.
This big delta is capital delta is pairing up, or what is it?
And that's a good question, but I'm not sure. Yeah, I'm not sure. It would seem so, huh? But I'm not sure. Yeah, I have to check and go to the paper. Maybe he discusses it. Yeah, that's a good question, but I don't know the answer. Okay.
So, sorry to keep hammering this.
Yes, no, please.
What happens in the limit as delta goes to 0? Do we get a structure that we're familiar with, I guess?
The only thing I can say is n is 0. So then it's sort of like n non-interacting pairs. So the delta must have something to do with interactions between the pairs. Interactions with the pairs I would think are repulsive. Okay. It's something I have to admit I never understood very well, the connection with this and with a Richardson scheme. Because this is more general in the sense, because you don't restrict yourself to a pairing Hamiltonian, right? You have a more general Hamiltonian, but you get an eigenstate, at least for the ground state, which satisfies a property of the pairing Hamiltonian, which the Richardson Hamiltonian does not have. So, and I think this connection is not being, well, at least to me, I don't fully understand it.
Can I ask maybe about this Richardson, like about this wave function? How is this connected to BCS function? Because it's it looks like familiar.
Yes,
Anyway.
it is familiar. This, in one sense, it has good particle number. This thing has good particle number, so there is no approximation with respect to particle number, because each of them is 2 particles and you sum, so you have an exact particle number. So then you would think, it's projected BCS, but even that is not true, because projected BCS will be projected from a state which is like this, with identical structure. And so this is a further refinement on projected BCS. Okay? Okay, so let me, I think I have finished with, so this is basically what I wrote down. I have an example, but let me go over that. Okay, I will not say anything about neutron-proton pairing. This will be discussed by Augusto. So I now, in the remaining 45 minutes or so, I would like now to come to the second here, which is quadrupole. So Elliott's SU3 scheme, and try to explain that. So I repeat here. So you have this was what I called Puhrmann's Hartree-Fock, so a very simple harmonic oscillator Hamiltonian, augmented with added to it a spin orbit and an orbit-orbit term, and then two body. We saw this can be solved easily if that is zero. Then I discussed a little bit if this two body interaction is the pairing interaction in a single J shell, many J shells. Right? So now I will come to when this two body interaction is a quadrupole interaction, and how you can find analytic solutions in that case. Okay. So, to do so, I first have to introduce a very old idea, which is due to Wigner, and this is known as the supermultiplet model. Or alternative as the SU4 model. So what Wigner, this was Wigner in 1937. Okay, what Wigner assumed was a Hamiltonian. We get back to symmetries now. Suppose you have a Hamiltonian and it commutes with spin operators. So this is S is the spin. Okay, we're back to spin and isospin. It commutes with the isospin operators, so T mu, and it commutes with some operators, which these are double tensors. They have two indices. Right, and I will explain what they are in a moment. So S mu, this is the spin, right? So it's, as you may recall, so you go from 1 to A, sum over all the particles of S mu K. Same thing for the isospin. So this I discussed at length when I was reviewing isospin. And then this Y, so this is now, you can guess what it is. It's a sum over all the particles, and where you have an S mu spin and then a T nu, all the particles. Okay. This is, I sometimes call this Gamow-Teller operators, because a Gamow-Teller transition is a transition where you go from neutron to proton or vice versa, and you change the spin. And so this is an operator that can do that. Okay. And so what Wigner assumed is these commutation relations to be valid. Okay. We will see that's not really the case, but let's accept this and see what are the consequences. Well, so you must have states which are labeled by S, right, the total spin. you have states which are labeled by T, the total isospin. Okay, as a consequence, and this is a bit less obvious, but of course you have rotational invariance also of the Hamiltonian, and so your Hamiltonian will be labeled by total orbital angular momentum L. Okay, one thing I forgot to say, you have now a collection of operators, S nu, T nu, and Y mu nu. These are three, you have three components here 9, so that's 15, and actually you can show that this is an SU4 algebra. Okay, and of course you have the usual scheme, so you have SU4, and the one which we know already from previous discussion is the algebra associated with the spin, so that will be an SU2 spin algebra, and there will be an SU2 associated with the isospin. This we also discussed. Okay, so you have some labels, and the label of course is S, the spin, and the label here is T, and you have some labels here, and that is the difficult thing about supermultiplet scheme. These are traditionally, I apologize, but yeah, these are traditionally labeled as lambda mu nu, and unfortunately I've taken here mu and nu. This has nothing to do with these labels. I'm not gonna change, but this is the traditional way of labeling representations of SU4. Okay, so now I'm not going to develop this in detail, the group theory of it. I would like to give you an idea. I mean, we know what this is, right? This is just the total couple. Yes?
Sorry, because I didn't get it. Could you tell us more why it's SU4?
Oh, because this is 3 operators, this is 3 operators, these are 9 operators. You have 3 components here, 3 components here. So that's 3 plus 3 plus is 15. These, I mean, this is a poor proof. Eh? But you just count the generators. It's 15. The number of generators of, I will write this here because it's not so important. This is the number of generators is, yeah. And for S, you just subtract the number of operators, so it's omega squared minus 1. If you wish, I could have added here the number operator, or whatever I call it usually, n, little n, okay? Right? The number operator, if I add it here, then I have U4, okay? So please do not confuse lambda mu nu here, which are labels associated with SU4, with these components, which even in my notes I did the same thing, so sorry. Okay, so now we understand S, right? This is the coupling of all the spins. We hopefully understand isospin. That's a bit more complicated, but we will have an exercise on this kind of business this afternoon. Okay. What about these guys? What is the meaning of these labels? And that is more tricky to understand. And it goes back to something which was discussed in detail by Rick. And I will repeat more or less what he said. What I will do is the simplest thing, non-trivial thing possible. I will look at 2 particles, 2 nucleons, in the P shell. And now I clearly say two nucleons. They might be identical, they might be one neutron and one proton. Okay, both cases are covered. And I want to do something simple, namely I consider a delta interaction, an attractive delta interaction between the two nucleons. Okay. One thing I would like to make sort of this problem, so you would have, in the usual way of thinking, you would have a P3 halves and a P1 half, and then you can put a neutron here and a proton there, or vice versa. But so you think, well, you have lots of possibilities. How do I work that out? This afternoon we will work it out in this way, but let me work it out in a simple way. I know this interaction, it does not depend on S, the spin. It's spin independent and it's isospin independent. Okay, so I can decouple the spin isospin part from whatever orbitally happens. What happens orbitally, right? I have to couple two particles in the P shell, and so, okay, how can I do that? So P, that means L equals 1, so P squared, it means right, I can couple to total orbital angular momentum 0, 1, 2, right? I haven't said anything about antisymmetry yet, okay? So now I know this for a delta interaction will be the most attractive, so let me say something here. So this will be, how do I do this? Yes, I think I will put here S and here L. Okay, I will have, of course, I can couple the spins for each particle is 1/2, so I can couple to S equals 0. Let me do it here. S equals 0 or 1, and then T equals 0 or 1. The isospins, same thing. Then remember the rule, right? This must be odd. This is something we derived in the first lecture. Because of antisymmetry, this, if L is even, then S plus T must be odd. Okay, so this is the rule of antisymmetry. So now we can come to the classification. Let's put here T equals 0 and here T equals 1. Okay, then here if L equals 0, S must be 1, and then L equals 2, S must be 1, and then L equals 1, this is possible as well, then S must be 0. And I hope I haven't made a mistake. So here the same thing, S and L. So here if that S must be 0, then yes, 0. Here this is 2, 0. This is 1, 1. So, okay. Then I have to work out what are the J's. The J's are the coupling of S and L, so it's a 1 plus. Here coupling is 1 plus, 2 plus, 3 plus. And here the coupling of this one is a 1 plus. Here the coupling of S and L 0 plus, 2 plus, and this is 2 is Z. That's funny. It's not what I remember. But it's correct, yes. So, I've worked out the spectrum without doing any calculation, just by sort of thinking what it should be. Yes? Yes, the order. There is one thing I don't know, but this one I do know. Right? Because you see, S plus T is even. L is odd. It means spatial part of the wave function is antisymmetric. I take a delta interaction. This is the argument Rick explained 2 weeks ago, or almost 2 weeks ago. Yeah, no, 2 weeks ago. Rick explained this, that the interaction in a state which is spatially antisymmetric, it's 0. So without doing any calculation, I know that this is 0. These levels are at 0 energy. And actually this afternoon we will prove that this is the case. Okay. The only thing, then I know, of course, the 0 plus, it's more attractive for a delta interaction than the 2 plus, right? But this one, this difference here is delta. I don't know without doing an actual calculation. But the important part is actually contained here. This is spatially, so you have spatial symmetry for all of those states. Here you have spatial antisymmetry. And actually now, do I remember the SU4 labels? Yes, I think I do. No. No, I don't remember. But the point is that these SU4 labels are different for the states here than they are for the states here. Okay? And so the idea that I would like to get across is that these labels here for SU4, they tell you something about, of course, the total wave function must be antisymmetric. That's a requirement. But then SU4 tells you, where do you put the antisymmetry? Do you put it in the spin isospin part of the wave function, or do you put it in the spatial part of the wave function? And a reasonable nuclear interaction will try to put the wave function in a spatially symmetric state. So those are favored. These are, sometimes this is called favored SU4 representation. Or IREP, I should say. Okay. Is this sort of acceptable to people? The other point I wish to make is the following, that you see here, if you do, and this we will also show this afternoon, you see here, so this is basically an odd nucleus, so you have 1 neutron and 1 proton in the p shell, and you see that you have a 1 plus state, which is t equals 0, and it is degenerate with a 0 plus state, which is t equals 1. Right, so the first order situation of a neutron and a proton is a degenerate 1 plus state, well, a 1 plus state which is degenerate with a 0 plus state. We will see, of course, this is not true, right? We will see at an example where these are shifted, and we will try to understand what are the shifts. And also these levels here, you see they are degenerate in energy, and in an actual spectrum they will not be degenerate, but they will tell you something about spin orbit splitting and about the relative strengths of interactions in the t equals 0 and the t equals 1 channel. Okay. So are there questions about that? No. So what has this to do with SU3? How many? Yes, okay. So we will come back this afternoon to this kind of situation. And some of the projects are also related to some calculation of this type. So, okay, so now let's do this a little bit more formally. So let's assume we have an entire oscillator shell, P shell, but it can be the SD shell, it can be the PF shell, and so on. And so the degeneracy of this oscillator shell is U4 omega. Okay, how do I count? The omega would be, for instance, for the P shell, omega is 1. Is 3, I want to say. So it's 2L plus 1. For the SD shell, omega is 6, and so on. Okay? And the 4, it comes from the fact that you have 2 spin states and 2 isospin states, right? Proton, neutron, spin up and spin down. Okay. So now, this business of SU4, actually it comes down to relating this. I have to, let me erase this. Let me first do spin isospin. SU4. As we saw, this can be reduced to spin in isospin. Okay, we know what all of those are. Spin, isospin, these are these super multiplet labels, which we have some kind of a feeling. So this is this is the spin isospin part of the algebra. And so now I just do multiply with the orbital part of the algebra. And what do we want to have? We want to have a classification where we come down to SO3 associated with the orbital angular momentum. Right, this is T S lambda mu nu. The labels here actually they are the same as those labels, but somewhat transposed, but it's not important. And so what we did so far was look at this classification in terms of spin, isospin, and symmetry and antisymmetry. And so what Elliott claimed is that actually the orbital classification can also be specified, and you can always put here an SO3 group, which unfortunately usually is also labeled by lambda mu. These are maybe I should change this bit. Okay, fine. Okay, so to what of a Hamiltonian does it correspond? So we have our H here. Actually, we take the kinetic energy. We have the harmonic oscillator. Okay, so this is plus or minus, I don't know what plus apparently. Right. I will take a two-body interaction, Q. We can go to a second quantization, so this we saw, you can write it like that, h bar omega times, we consider an entire harmonic oscillator shell, so P, SD, PF, etc. And here we get the sign again, QQ. I don't, well, there must be some strength here, QQ. Plus some, I don't know. Well, let's put G2 because it's, and this is the quadrupole operator. Okay. So this was the Hamiltonian which was considered by Elliott. Right? As you can see, there is no spin orbit, there is no orbit-orbit, That is a major problem for this scheme. It's a major problem for SU4, and as a consequence, it's a major problem for the SU3 scheme, that you don't have, I mean, in this derivation, you don't have a spin orbit. You have an LS coupling scheme. Okay, so now the only thing to be specified is what is this quadrupole operator, and that is a little technical. Now, this was discussed by Mark, actually, but Mark gave the expressions of this quadrupole operator in terms of the quanta. Okay? Now, we want to do something different. We want to give an expression of the quadrupole operator in terms of particle creation and annihilation operators. That's a little bit more tricky. So, in this scheme, what is a particle creation operator? So, it's a dagger, so it's a fermion. Okay, now it's LS coupling, so I will give a label L for the orbital angular momentum and its projection, then spin 1/2 and its projection, isospin 1/2 and its projection. Okay, and then there are annihilation operators, and then there are these operators which are just, yeah, this is very long to write with. This is a phase, right? What did I do? Yes, plus. Huh? And here A. Okay, and so then I want to construct operators. The entire algebra for omega is generated by here I can couple to total angular momentum L, total spin S, total isospin T, okay, and then with projections MS and MT. These, if you look at all the possible values of LST, no restriction because there is no antisymmetry, since this is creation, that is annihilation, then you should find for omega to the square operators. Okay, so now how do you construct this algebra? This is just taking by scalar combinations in the angular momentum, in the orbital angular momentum. You put this to 0. And how do you construct the operators of U omega? This is what interests us. You take scalar operators in the spin and in the isospin. So these will be the generators of U omega. Okay. And then how do you construct now the generators of SU3? This is a sort of a trick. So this is a conventional factor which you take in front. This is the quadrupole. There is a little thing I have glanced over which I will come back in a moment. But let's suppose for the moment that this is just the quadrupole operator, as you know, which is sum over k r squared k 2 mu, right? The k I k, okay. Put it in. So this is a one-body operator. The Q is a one-body operator, and so this is then the expression for the quadrupole operator. Okay, and this is now, this comes to things we have discussed in angular momentum, right? In principle, we can calculate reduced matrix elements. Yeah, I should put here also n prime. Okay, but we're in a shell where 2nl is a constant, right? We consider one major shell, so if we know n l, we know n and vice versa. So this now becomes a matter of calculating matrix elements. So you have two matrix elements in particular, so you have this one. Wait, this prime. Yes. Well, the expression is given in my notes, so. So this is, for instance, one thing you can find in this book of Suhonen. So L, K, L prime, 0, 0, 0. And then you have radial integrals to calculate, right? So you go from 0 to infinity. This is r squared, so you have this is the volume element, and this you can calculate in the standard fashion. Okay, I will not write the expressions there in the notes. And that gives you the quadrupole operator. And so now you can look, the expression is given in the notes. So it's a long expression, a summation over L and L prime. I'm not going to put it on the blackboard, but it's in the note. Okay, and so now one last thing. So this is the quadrupole operator, and so then the angular momentum operator, well, it's a vector, so it has three components. There is only one way you can make that. So it must be scalar in spin and isospin. So you have it's 1/2. Ah, there is a sum over L. And then there are some factors which I believe it's like this. Yes. Oh, sorry. I haven't put all the quantum numbers here. Okay. Then you look at commutation relations. Yeah, I'm sorry, this derivation is a bit long, but it's sort of, since it's related to rotational features in nuclei, it's rather important, SU3. So, okay, so then you have Q in L, and you can of course convince yourself that L, again I will not write it explicitly, right, this is proportional to this is mu. So this is some alternative way of writing commutation relations for the angular momentum operator. So mu q, this is proportional to 1 mu 2. This should go back to q. And then the last one, this is the this is sort of trivial. This is because it's the angular momentum, so you should get the same operator back here. But this is the one which is important, because it goes back to the angular momentum. So the thing closes, so you have 3 plus 5 generators, and so that is, it generates the group SU3. So you could add another one, which is the number operator, then you would get U3. Okay, then you have 9 operators. And so now you get back to the same idea. So you have identified an algebra in between this orbital algebra, so U omega, and the orbital angular momentum algebra, so this is L. We have identified this one, it has associated quantum numbers, right? This is, this basically these SU4 quantum numbers, sort of transposed. And what was I going to say? So the quadratic Casimir operator now will lead to a solvable Hamiltonian. And the quadratic Casimir operator, it can be shown, it's a linear combination of QQ plus L squared. So I have an SU3 limit of the shell model which has a quadrupole operator in the harmonic oscillator Hamiltonian. And so that's the main goal, that was the achievement of Elliott. Okay. So this I all did. This is the same thing as I did for the P shell, but here it is done for the SD shell. It becomes a little bit more complicated. And here are the labels that are associated. So you have 2 particles, and so one is in this spatially symmetric situation. You see that the angular momenta are even. This is spatially antisymmetric. There is a 2, but this is S and D. It's like the mixed symmetry states in the IBM 2. So you have 1, 2, and 3. Okay, and it's spatially antisymmetric, and these are the favored in the SU4 scheme, and these are the unfavored. And usually people sort of look at the favored. Okay, so this is the same sort of classification, but for the SD shell.
So
Yep.
This punchline of the nuclear interaction is short range, attractive, therefore favors maximal. This is because we showed that for the attractive delta, and this is the nuclear interaction is close to an attractive delta, so we can kind of pull some of those conclusions about the attractive delta to the real nuclear interaction.
Yes.
So can we conversely say the opposite, like for maybe these states that have these really loosely bound systems, that maybe the nuclear interaction is becoming further away from an attractive delta, and maybe we get more spatial asymmetry?
Yes, I mean, if that is the case, I don't know about whether this is really the case if you go far from stability, but if that is the case, right, that you have that the short range character of the interaction is lost, then this argument is valid in the sense that these states which are here unfavored, they become less unfavored than they were previously. It's a generic statement. Okay. And this was done by Phil Elliott, so in '58. This was sort of, people were puzzled, I think, more than they understood what was happening, because this was before the application of SU3 in particle physics. This was before the Eightfold Way. But the main point is that you get rotational features in a spherical shell model, right? So this is the thing that, of course, that this was discussed by Mark in more realistic situations. But if you do this approximation of an interaction which is quadrupole, right, which in the presence of protons and neutrons, this is a first order approximation, pairing plus quadrupole. So if you have a quadrupole component, you get to rotational features. And this was the achievement of Elliott to develop this in the spherical shell model. There is one point which I sort of glanced over. This was mentioned by, stressed by Mark, is that actually if you want to confine yourself to one shell, as did Elliott, so one major shell, you cannot just take the physical quadrupole operator. The physical quadrupole operator would be this one, right? Where you have a sum over y2 mu, which depends on the particle position. But what if you want to confine the analysis, you have to add to this this contribution, which is written in terms of the momenta. Okay, if you take the physical one, then, as Mark showed, you will have these matrix elements, but you will also couple to, I think it's the oscillator n plus 2, right? So because you add two quanta. Okay, so this is one point, but luckily, I mean, the matrix elements of these guys, they're proportional, so you can do this analysis, but just taking the spatial dependence, and you get the general. Incidentally, if you would do this for the SD shell, right, the expressions that I give in the notes, this was discussed remember in the IBM, what was the quadrupole operator for SU3? It was an S boson D plus D dagger mu S coupled to 2. And then there was a minus square root of 7 over 2 D dagger coupled to 2. And this sort of came from the sky, right? Why was it square root of 7 over 2? If you go to the expressions here for S and D, you will precisely find this coefficient, square root of 7 over 2. Right? But this is general, so you can do it for the PF shell if you wish.
One question.
Yes.
What about the constant or parameter that we have next to the quadrupole interaction?
This one.
Yes.
So this is the strength of the quadrupole interaction. Right? It's a parameter. It's the usual. Right? If you remember the discussion, we always had the strength. Also, the pairing had the strength. Right? A G. So here, this is the strength. I would imagine, so G2 is positive for an attractive quadrupole interaction. Okay, I think I should be finishing. I guess, yes, I have to. This most of the things I said. Right, this is, yeah, maybe one point, this is in the 50s, so one had the spherical shell model, which was successful, but then you also had the collective model which described rotational features. And at that time it was not obvious what was the connection between the two, and this is sort of the first, well, there were some numerical calculations already, but it's sort of the first explicit connection that was established between rotations and the spherical shell model. So it is another example of a spectrum generating algebra of a dynamical symmetry. Right? What is the problem? The problem, this I mentioned, is this is an LS coupling scheme. It's not a JJ coupling. So in principle you have, well, not in principle, I mean you have to put the spin orbit splitting to 0, otherwise this doesn't work. And so there were applications to rather light nuclei as D shell, but if you go to heavy nuclei then you have problems. And this point I mentioned that your Q is the algebraic quadrupole operator, so which is a momentum and a position dependent on R and on P. Okay, I don't think I will. So as I argued, I mean there are important terms that break SU4 symmetry and as a consequent SU3 symmetry, spin orbit, Coulomb, and any spin dependence of the nuclear interaction. And this can be shown, but I don't think I want to go into this because it's time to wrap up. Yes, maybe one thing I would like to mention. Yes, let me show this figure. So there is this problem that SU3 is a LS coupling. So you require that this is for the SDG shell, right, as an example. You require that G7 half and G9 half are degenerate, D3 halves, D5 are degenerate, S1 half is on its own, okay? So there are now two ideas to sort of, this would be a poor approximation because we know that G9 half, for instance, is in the shell below, right? So it's rather separated from G7 half. So this would be a poor approximation, but you can sort of have two ideas. And this I would like to show in a picture. One is called pseudo SU3. Let me start with that one, where you say, well, this guy is apart and I do not wish to consider it. For instance, if you're only looking at level above F7 half, above 50, this would be okay. And then that is true, actually. D5 half, G7 half are rather close in energy. So let me consider this as a pseudo doublet, right? The spins are okay, 5 halves and 7 halves. And let me assume, or let me consider this as something which comes from F. So that's L equals 3, coupled with the pseudo spin that will give 5 halves and 7 halves. And the same here, S1 and D3 halves. Actually, that's not a bad approximation. If you forget about the unnatural parity orbit here, which is H11 half, these degeneracies are more or less there in the spectra. And so this is, you can then follow the whole classification in terms of pseudo SU3 and pseudo SU4, and it works out more or less the same. Another, and this is called quasi, so this is from the 60s, Arima and co-workers did this together with Hecht, or simultaneously with Hecht. This is another idea, this is due to Zucker. And so here you say, well, I have the same kind of shells, but let's now assume that these are intermediate in energy, and actually you can then look at the coupling matrix elements, and you can sort of approximately say that these levels would couple to each other, and these levels would couple to each other. And so the important thing in the SU3 scheme is that you have delta L equals 2, right? That you go from G to D to S, and this is preserved here. You go from G to D to S, and you can construct an approximate scheme, which is called quasi SU3. Right, so you have some feeling for what these terms mean. Okay, I think that's what it is, and